What's that? He doesn't? He's tired of pvalues? All right, so we've actually got more time than my other class. So this is fantastic. So, all right, today we're going to talk about 12.1, which is the chi-squared goodness of fit test. Okay? And the idea is we want to see if the distribution matches some preconceived idea. Okay? For example, maybe you wanted to see if your die was fair. You got a six-sided die, you would expect them all to be equal numbers, right? So that would be an example. All right. So let's do an example. We're going to start with an example. I'm going to try to do this without giving away the answer right away. I think I gave it away in my other class. Share screen. Okay. So let's say, for example, that an economist wants to know if the distribution of U.S. residents is the same in 2000 as today. In 2000, 19% were in the West, 22.9% in the Midwest, 35.6% in the South, and 22.5% in the West. Oh, 19% are in the East. Sorry, that first one should be East. All right. Okay, so economist selects 1,500 random households. Okay, and finds the following. So we've got a region here. I've got the Northeast. Oh, this is technically that's the Northeast. I can't read my stuff very well today. Northeast. Okay. So I've got the Northeast. I got the Midwest. I got the South. And I got the West. And we observed 274, 303, 564, and 359. Okay? All right. So the first question, if this was on a test, that you should ask yourself, is this categorical, quantitative, or regression? It's what? Categorical because we're living in one of the four areas. Okay. Next question should be, what'd you say? Your null and your alternative hypothesis. Now, today's going to be an exception to the rule. Okay. Normally, I'm looking for an equation here, a letter and an equation. Okay. With the chi-square goodness of fit test, I'm going to break that rule. Okay. So don't keep breaking it, but you can break it for this. Okay. So here's what's going to be the null hypothesis. I'm just going to give it to you. The distribution has not changed. Okay. Now that's consistent with, remember, let's talk about a generic null hypothesis. What does a generic null hypothesis means? No change, no difference, fair coin, that kind of a thing. Okay, so we're consistent in that case, but this is the one case where I'm going to let you break the rule. You can actually write a sentence for this. Okay, now the alternative hypothesis would be distribution has changed. Okay, now this is the one test, and I'll explain this when you see the calculations. It's going to make more sense in a minute, but this is going to be what we're going to call a right tail test. And I'll explain why that is in a minute. Okay? It's always going to be a right tail test. Okay? Now, the next question is, what kind of test? Is it a z, a t, a chi-square, or an f? And it's going to be a chi-squared because I told you that at the beginning of the class. But how would you know that if I hadn't told you on the test what it was going to be? And not just any chi-square test. We've got multiple chi-square tests now. So let's be more specific. What kind of chi-square test is it? It's going to be a goodness of fit. Okay, because I gave that away at the beginning of the class. But how do you know? We're comparing distributions. We want to see if the distribution matches some preconceived idea. Here's my preconceived idea. Right there. Okay, so notice these are in percents, these are in raw numbers. I should either convert these to raw numbers or whatever. We're going to do it this way. So let's talk about the expected. If the distribution had not changed, what would you expect? You would expect 19% times 1,500 households, right? And you would expect 0.229 times 1,500 and 0.356 times 1,500 and 0.225 times 1,500, and hopefully that adds up to 1,500. It does. And that does too. Okay. Oh. That's a problem. Where's my typo? Oh, this one should be 359. Okay. Good thing you check your math. Okay, find your typo. Let that be a lesson to you on the problem. Okay. All right, now, okay, so here's where I need to give you the equation. Okay. So with the equation of the chi-squared goodness of fit test, chi-squared equals the observed minus the expected squared divided by the expected, and we're going to add them up. Okay, so that's your new equation that we're going to be using today, and we're going to talk about degrees of freedom. Here I'm going to give you what's your degrees of freedom. -1. That's not our rule today with the chi-square goodness of fit test. Okay, the chi-square goodness of fit test degrees of freedom are number of rows -1 times number of columns -1. Okay. Now, as I look at this, how many rows do I have? 4. 4 minus 1 is 3. How many columns do I have? 2 minus 1 is 1. 3 times 1 is 3. Okay. So in this case, let me share here. So I'm going to do chi-squared equals the observed minus the expected squared divided by the expected, and my degrees of freedom in this case is going to equal 3. Okay? All right, so now here's how we're going to do this. Okay? I'm going to create a column here called observed minus expected squared divided by the expected, except for I really should I'll use parentheses, but okay. So equals the observed minus the expected squared divided by the expected. Okay. I am going to copy that formula down, and I'm going to add them up. Auto sum. Oh, no, don't want to add that up. I want to add this up. Okay. Now I got the value of 8.25. Now let's think about this for just a minute. Okay. This is why this is always a right-tailed test. Let's pretend there wasn't much difference. Let's pretend, for example, this was 275, and this was 304, and this was 563, and this was 358. Okay? So you can kind of see visually there's not much of a difference, right? Look at my sum. My sum is very close to 0. So there's not much of a difference, like clearly, obviously. Now the question is, if I go back the way that was, is that a big difference? Okay? So the idea here is, if I draw a picture, okay, this is why this is always a right-tailed test. Okay? I've got my chi-square distribution here. If there's no difference, my sum is going to be very close to 0. Okay? If there's no difference, you're going to have a very small sum. So there's no, on a goodness of fit test, it doesn't really make sense to do a left-tailed test. It only makes sense to do a right-tailed test. Okay? Because that's going to tell you, oh, there's some big differences going on. Does that make sense? Okay? Yes?
So you couldn't have, like, you could have 0, but you couldn't have 1.
You couldn't have 1, you could have 1.
So it would be like 100% different.
Well, like, for example, we're 8.25. We've got a sum. No, I'm just talking about the sum.
Oh.
So I've got a sum. Now the question is that a big difference or not? I don't know. I didn't memorize my chi-square chart. Okay? All right, so at this point, we've got our sum. Now the question is, what's the next step? So in this case, my chi-squared test statistic equals 8.25, or I'll do it this way, equals that number there. Okay, I got 3 degrees of freedom. What's the next step that you're supposed to do? What? Compare, well, before you compare, you got to find your p-value, right? Then you can compare. Okay, so my p-value, what's the command for p-value? Equals chi-squared dist. And it's going to be a right-tailed test, right? This is going to be a right-tailed test. I'm going to put this number in. My degrees of freedom is 3. Okay? So I got a p-value of 0.04. Didn't give you my alpha, so what do we assume our alpha is? 0.05. So now, like Gabriel says, we're going to compare, and we're going to reject or do not reject? Reject the null, which means there is evidence that distribution has changed. Okay? What's the next obvious question? Where has it changed, right? Okay? Now, let's go back to here. Let's go back to this, okay? Look at those numbers. Which number contributes most to that sum of 8.25? It's the 4, right? Which is the Midwest, okay? Now, let's think about what's going on here. I expected I would have got 343 people. I only got 303 people. What's happening in the Midwest? People are leaving, okay? What's the next biggest number? The South, 1.68. South, that's the next biggest number, okay? What's going on in the South? I expected 534, I got 564. People are moving out of the Midwest into the South, okay? What's happening in, or what's the next biggest number? 1.36. What's happening in the West? I expected 337, I got 359. People are moving to the West, okay? This is my smallest number. This is the one in which people are staying put the most. But what's happening in the Northeast? I expected 285, only got 274. People are moving out of the Northeast and the Midwest. They are moving to the South and the West. Does that make sense? Okay? That should be extra credit on your test. You can tell me that. Okay? Don't just tell me that the distribution has changed. Tell me what's going on. Okay? And I think I probably will put extra credit on that if you do that. Okay, yes.
Do you ever have to check for the sample size?
You know what, they didn't, I don't think they mentioned that. Sample size was 1,500, so I wasn't that worried about it.
Yeah, I was wondering.
I don't remember them even saying anything in the book. We are going to do a chi-square independence test, I think, on Monday, and I'll probably check sample size there. Let me see if I can look here. I don't remember them saying a word about sample sizes on this one. My guess is on Monday, I'm pretty sure on Monday, yeah, we're going to do an independence test. I'll talk about that. Monday is going to be an independence chi-square test. And we'll talk about sample sizes on Monday. I would assume the same rules apply. Basically, your expected counts have to be at least 5. I'll talk about that. But I'm not going to worry about that today. Okay? All right, we got 5 minutes left. Would you like to jam through one more of these?
I thought like another. Yes, let's do another.
Okay, if you want to leave, I'm going to let you go 5 minutes early. If you want to stick around and do well on the test, you should stay. Here, we'll pour that guilt on you. Okay? Yes, Chris.
Would we ever be asked to do one of these with Alex?
Would we ever ask what?
Would you ever have to do this with Alex?
Unlikely. Yeah, this is probably more of a computer question.
Do one that we can do, or would we have it set?
Oh, I don't know. I'll think about that over the weekend. Probably, I don't know. Probably Excel, but I don't know. I haven't looked. That's Monday. I got a weekend, just like Kendall was saying. I want a weekend too. Actually, my weekends, I'm going to catch up on your tests, so that's what I'm going to do. All right, so let's do one more. An obstetrician wants to know if the proportion of children born on each day are the same. She obtains a simple random sample of 500 births as shown in the table below. Is there a difference by day? Use alpha equal 0.01. So, did you know this is really cool? Sunday, watch this. Excel can be pretty cool. It will count for you. Now that's impressive, okay? Now, Sunday, we got, so this is our frequency, 57, 78, 74, 76, 71, 81, 63. And, okay, so that's what we're given, okay? So let's just go through all the steps really quickly, though, because we've only got a couple minutes left. Okay, is it categorical, quantitative, or regression? Categorical, it's day of the week, right? Your null hypothesis is no different. So children born each day are not different. And your alternative, there is a difference, okay? It's going to be the chi-square test, goodness of fit test. Goodness of fit test. In order to do the goodness of fit test, I've got to figure out my expected values, right? What would I expect for Sunday? 1/7 of them. 500 divided by 7, right? Oops, not 50. 500 divided by 7. What happened there? 500 divided by 7. God, what's wrong with this? It still gave me 50. Okay, you would expect 71.4 each day, right? Okay, so we're going to do the observed minus the expected squared, etc. equals the, use parentheses or you'll mess this up, observed minus the expected squared divided by the expected. Okay, I'm going to copy that down. I'm going to find my sum, 6.184. Okay, I also need my degrees of freedom, right? What's my degrees of freedom? 6 times 1 is 6. Okay, I'm going to find my p-value, which is chi-square dist on the right tail. That number, degrees of freedom, 6.40. Okay, so therefore, do not reject. And your conclusion is number of children born each day is roughly the same. Okay, now if there was a difference, what would you say the difference was? That's your biggest number. Okay, you expected 71, but only 57 were born on Sunday. Why do you think babies aren't born on Sunday? Because the doctor wants Sundays off. Come on, I want to go to church. Leave them alone. Okay? We're going to start you on some other day of the week. What's the next biggest number? Friday. Because I got my weekend coming up, we're going to start you today. Okay? Get that baby out of here so I got my weekend free. But it's not a significant difference. Yes?
I thought you said that we want to make sure that our statement is not too strong. And that
yeah, that is a little bit of a stronger statement. But yeah, not a significant difference for the children born on the day of the week. Yeah, that's fine. That's probably a better way. Okay, I was in a hurry, so I was going fast.
Second
Yes.
question. Would you ever have more than 2 columns?
I don't think on this test, but yes, potentially.
But not for us?
On Monday's test, we're going to do an independence test. You will definitely have more than 2 columns.
Okay. But for like the goodness test, you just have to.
Goodness, I think most of these are probably just going to be 2 columns. Yeah. Okay. All right. See you all on Monday. Have a great weekend.